This section will cover the core initialization process. There are 3 steps to initializing a system: CPU, boot device, and OS initialization. CPU initialization initializes the CPU to a known state. That is what we're going to cover in this section of the course. Next, you would normally go to initializing devices needed to bring up the operating system, and then you would start the OS, and the OS would initialize itself. These last 2 steps will not be covered here. You should consult your OS manual for more information. The first thing I recommend doing is to initialize the general purpose registers. This is not strictly necessary. The CPU will function fine without it, but it is good software practice to do it. To initialize the registers, the code will move a 0 using the ever-constant 0 register into the remaining registers. It does this by using the OR instruction. You can also write this code using the move instruction, because the move instruction is really an alias for the OR instruction. The coprocessor 0 status register controls the operating modes of the processor. The status register plays an important part in the initialization process, so I will go into detail here. Bits 28 through 31 are the coprocessor usable bits. These bits control access to coprocessors 0 through 3. Bit 28 controls access to coprocessor 0 when the CPU is in user mode. Bit 29 controls access to coprocessor 1, usually the floating point processor. Bit 30 is reserved for implementers that want to add their own special coprocessor. You want to disable all these bits during the boot process and have the OS enable them if it will be using them. The reduce power bit, number 27, can be used to send a signal to an external clock that tells it can slow down to reduce power. This is usually used in conjunction with the wait instruction when the CPU is in an idle state. On boot, the CPU should be at full power, so this bit should be cleared. The floating point bit controls the number of FPU registers that are available for use for compatibility with MIPS 1 ISA. When this bit is cleared, the CPU floating point unit is in compatibility mode and should be cleared and later controlled as the OS sees fit. The reverse Indian bit, number 25, reverses the Indianness of instructions fetched when set. This should be cleared and left up to the OS to switch. As a side note, there is no known OS that sets this bit. The MX bit, number 24, enables DSP instructions. This should be cleared and left to the OS if required. The boot exception vector bit, number 22, controls which set of exception vectors are used. Vectors were covered in the exception section of this course, so I won't go over them here. This should be cleared so that the normal exception vectors will be used. The TLB shutdown bit is set by the processor when it detects an attempt to create a duplicate TLB entry. It will also generate a machine check exception. The exception routine should correct the condition and can clear this bit. This bit should be cleared to initialize it. The soft reset bit, number 20, would indicate a soft reset condition. However, in our cores, it is hardwired to 0 because soft reset is not supported. The NMI bit, bit 19, is a read-only bit that is set when the CPU gets a non-maskable interrupt. The core extend bit, bit number 17, enables the use for the core extend instructions. Bits 8 through 15 are the interrupt mask bits. View the exception section of this course for more information. For now, these should be set to mask all interrupts and left to the OS to clear as device drivers are initialized. The kernel user supervisor bits 3 and 4 should be cleared, which puts the CPU into kernel mode. The error exception mode ERL bit 2 is set by the CPU at power up, NMI, or cache exception. It should be cleared. The regular exception mode EXL bit 1 should be set to keep us in kernel mode. And last, the interrupt enable bit, bit 0, should be cleared to disable interrupts and left to the OS to set when it has initialized its drivers and is ready to accept interrupts. To set the status register just described, load the immediate value of FF02 into the general purpose register and use the move to coprocessor 0 instruction to move the register value to the status register. The boot code needs to disable and clear watch point exceptions. There are 4 pairs of watch point registers. The watch low registers are coprocessor 0 register 18 select 0 through 3. Writing a 0 to the 4 watch low registers will disable all watch points. The watch high registers are coprocessor 0 register 19 select 0 through 3. Writing a 7 to the 4 watch high registers will clear all watch conditions. The cause register describes the cause of the most recent exception, enables vectored interrupts, and enables the count register. The boot code should clear the cause register so there will be no spurious interrupts when interrupts are enabled. The config register controls, among other things, the cacheability of KSEG 0. Setting bits 0 and 1 set KSEG 0 to cacheable, write back, and write allocate mode. The compare register acts in conjunction with the count register to implement a timer and timer interrupt function. The timer interrupt is an output of the core. The compare register maintains a stable value and does not change on its own. The count and compare registers need to be initialized so the OS may later use them for timer interrupts. Clear the count register by setting the counter to 0. Setting the compare register to the highest number possible will give us time to do the remaining steps in the initialization of the CPU. It also clears the timer interrupt, which in this case is redundant because all interrupts have been cleared and disabled when we cleared the status register and cause registers. Now we are set to initialize the caches and the TLB. Until they are initialized, you can only use uncached and unmapped memory regions like KSEG 1. Remember, the boot vector is in KSEG 1. The initialization of the caches and the TLB is covered in the cache and TLB sections of this course. Just like the general purpose register set, we also want to initialize the shadow register sets to 0 if we have them. First, the code will read the shadow register set control register. Then it will extract the highest shadow register set number, which is the number of shadow register sets. These bits 26 through 29 are extracted using the extract instruction. It will start extracting from register 11 at bit 26 and go for 4 bits and place the value in the low order bits of register 12. Now the code sets up a loop. First, check to see if there are any shadow register sets to clear. If there are, use the number in register 12 to set the shadow register set we will be clearing. The code this is by using register 12, which holds the number of the highest shadow register set to be cleared, and inserting it into bits 6 through 9 of the previous shadow register set field of the shadow register set control register. This was read into register 11 in a previous step. Then, the move to coprocessor 0 instruction moves the value in register 11 into the actual shadow register set control register. Setting the previous shadow register set causes all writes using the write previous general purpose register to be written to that shadow register set. The code zeroes out each register in the set in turn. After that, the code branches to the beginning of the loop and decrements the highest register set counter, held in register 12. The code has done all initializations for the CPU and is ready to execute the next boot step. The code loads the starting address of the next part of the code into the error program counter. Note, the address in this example is in CaseEx 0 memory section, so it is cacheable, and once the code is jumped to, it will be running out of cache. The actual address will be determined by your code, but it should still be in CaseEx 0 memory region. The code executes an EHB instruction to clear any hazard barrier, and then the return from exception instruction to exit exception mode and jump to the address held in the error program counter. This is the end of the CPU initialization section.